Errors and Uncertainties. Part 2. Estimating the uncertainty. Our example here is timing 4 oscillations of a pendulum. Normally we would time more than 4 oscillations, but I want to keep the video short. So I let my pendulum go, and as it crosses the equilibrium position, I start the clock. When it crosses again in the same direction, then that means 1 oscillation, and then each time it does so I count another one, so this is 2, here's 3, and when it gets to 4 then we will stop the clock. And when we do so, we'll think about the uncertainty. So our reading on our clock is very precise, 20.08 seconds. So the clock has a high resolution, and we might think, well, just like with our ruler, the smallest gradation on our scale gives our uncertainty. But if you think about it, we haven't really measured this to plus or minus 0.01 seconds. We had to start the clock at the right time. We had to stop the clock at the right time. So how do we know how much uncertainty is in the result? Well, the answer comes from repeating it. So here I've made an axis for time. So my measurement, which was 4 time periods, 4t in seconds, I'm going to plot values of that I measure along here. And here's the one I showed us measuring a moment ago. This red dot is my initial measurement of 20.08 seconds. If I just did that measurement once and then said, well, the resolution of my clock gives me my uncertainty, then I would be saying I'm confident that the true value for 4t is within plus or minus 0.01 seconds. So that's this very narrow range here. But that doesn't sound realistic. We have uncertainty that's brought in from starting the clock and stopping the clock, and both of those are going to vary in a way that is random. It's going to be a little bit different each time. So how do we know what a much more realistic range for the measurement is? What's our better way of measuring uncertainty? Well, the only way we can be sure of it is by repeating the measurement. So if we imagine that I did this measurement again, and this time I got 19.57 seconds, well, that would be a dot over here. Straight away, we can see that that's not within this little range that we had before. So, we've got a pretty good indication that actually we had a terrible underestimate of the uncertainty. So let's just keep doing repeats. So I measure it again and I get 19.88, that's there, and so on, and I keep on making more and more measurements of 40. And eventually I have a few dots there, and the more I have the better, the more I repeat this the better, but of course that makes my experiment take more time. And by looking at them I can see a sort of range of values, and I would say, well, I'm pretty confident that my real value for 40 is somewhere around here in this range. So what I'll do is I'll take the average of them, just the mean of them, and that will be the value I will write down for 40. So here's the average. It turns out to be right there. Then I will take the range, that is the smallest value subtracted from the biggest value, and I will half that, and I will say my measurement could be up to half of that range either side of the average. And if I do that, then the uncertainty looks something like this. And this gives me something that is much more realistic. So now I've got an uncertainty that is plus or minus half the range of my measurements. Now, it's still only a way of estimating the uncertainty. It's not a perfect answer, but this is the way that you should do for IB physics. This is the way you should do for your investigations, is uncertainty is plus or minus half the range of a repeated measurement. So let's show that same example with a table of results. So here I've got a little bit of my table of results. So I've got one value for length of my pendulum, and here's my results for 4t with their unit in seconds, and I've split that column into 8 subcolumns for the 8 repeats and then a space for the mean. So the first thing I'm going to do is take my 8 repeated measurements, find the mean of them in the usual way, just add them all up, divide by 8, and the number I've got here is what my calculator gave me. I haven't rounded it off at all, but probably there's no point in writing down all of these decimal places because I don't really know the value to that kind of precision. So to find out how much precision I can write down the value to, I need to find my uncertainty. For that, I find the range of my measurements. So I literally just look along the table of results and I find the biggest measurement, which is here, 20.25. There aren't any numbers in those repeated values that are bigger than that. And I find the smallest one, so that's 19.27. And then I subtract those to get the range, which comes out as 0.98 seconds. Now, that's the spread of the whole thing, but my value could be up to half that spread either side of the middle, either side of the mean. So to get the uncertainty, which we always write as plus or minus a certain amount, I'm going to half that range. So I'll just divide that by 2 and I get 0.49 seconds. Okay, so because I could be up to 0.49 seconds, up to about half a second out from the mean that I've calculated, there's no point in writing down the hundredths of seconds or thousandths of seconds that I got from my calculator measurement. So when I write the mean into the table, I'm going to round it off to 19.8 because that is the last decimal place that actually has any meaning when you look at the kind of uncertainty in my measurements. So 19.8 is the value I'll write in for my mean. I'm also going to round off the uncertainty. There's no point in writing down the uncertainty lots of decimal places. What we're saying here is that the uncertainty is around about 0.49 seconds, or around about half a second. And the convention with uncertainties is we always round them to one significant figure, unless the first digit is a 1, in which case you'll write down a second significant figure. So in this case, I'm going to round it to 0.5. So my final answer for what 40 is that I'm estimating it's 19.8 because that was the mean of my measurements, but I'm saying I'm confident it's within plus or minus 0.5 seconds of that 19.8. So in other words, it's somewhere between 19.3 seconds and 20.3 seconds is my estimate of what 40 is.